What is the single most persistent dream woven into the fabric of human consciousness? It is not the dream of wealth nor of power, but of the journey. The unshakable primal urge to see what lies beyond the next hill, across the next ocean, past the next star. For millennia we were a species bound to the familiar shores of our own world, our maps ending in illustrations of impossible monsters and the stark warning, "Here be dragons." Yet we built ships from wood and courage, and we sailed into the mouths of those monsters anyway. We conquered the oceans, we mapped the continents, we tamed the skies. With each frontier crossed our gaze lifted higher, until we were staring into the infinite black, the final unconquerable sea. Space. The very word evokes a silence, a scale that defies the architecture of our minds. We sent our first emissaries, robotic pilgrims and human pioneers into the near void, touching the moon, tasting the dust of Mars, and flinging probes into the great emptiness. They sent back postcards from the abyss, images of staggering beauty and profound loneliness. But these were mere footsteps in our own cosmic backyard. The true journey, the one that hums in our fiction and fuels our most audacious ambitions, remains tantalizingly out of reach. The journey to another star. The difficulty isn't one of will, nor even entirely of technology. It is a problem of time dictated by a law as fundamental as existence itself, the speed of light. It is the universe's ultimate velocity, a cosmic speed limit enforced with absolute authority. 300,000 kilometers per second. It sounds impossibly fast, a speed that could circle our entire planet 7.5 times in a single heartbeat. But against the tapestry of the galaxy, this magnificent speed is rendered a pathetic crawl. The nearest star to our own Proxima Centauri is over 4 light-years away. A journey aboard our fastest spacecraft would take not years, not lifetimes, but tens of thousands of years. Our ships would become generational tombs, their crews living and dying in the cold dark, their distant descendants arriving at a world their ancestors only ever saw as a point of light. Our own Milky Way galaxy is 100,000 light-years across. To traverse it, even at the speed of light, would be a pilgrimage of ages, a journey so long that civilizations could rise and fall on Earth in the time it takes for a single message to cross from one edge to the other. The universe, in its sheer soul-crushing immensity, has constructed the most perfect prison. Its walls are not made of stone or steel, but of space-time itself, and its warden is the tyrannical constant of light. We are islanders staring across an ocean of such unfathomable breadth that to even dream of crossing it seems an act of profound, beautiful insanity. Unless, that is, we have misunderstood the nature of the journey itself. What if the answer isn't to build a faster ship to cross the ocean, but to somehow fold the ocean in half, touching 2 distant shores together for a fleeting, miraculous moment? This is the revolutionary idea that forever changed our perception of the cosmos, an idea born from the mind of a man who saw reality not as a static stage, but as a dynamic, flexible fabric. Albert Einstein, with his theory of general relativity, didn't just give us a new understanding of gravity. He handed us a new universe. He revealed that space and time are not separate and absolute, but are woven together into a single 4-dimensional continuum space-time. And this cosmic fabric, he showed, is not immutable. It can be bent, stretched, warped, and compressed by the presence of mass and energy. Planets and stars are not so much moving through space, as they are rolling along grooves and valleys they themselves have created in it. Within this radical new vision of a malleable reality, a tantalizing possibility emerged, a ghost in the mathematical machine, a loophole. In 1935, Einstein and his colleague Nathan Rosen were exploring the bizarre implications of their own equations, pushing them to their absolute limits. They wondered what would happen if you took space-time and bent it so severely, so profoundly, that you punched a hole clean through it. The result was a theoretical structure, a bizarre and beautiful solution to the equations of relativity which would later be known by a more evocative name, a wormhole. The concept is as elegant as it is mind-bending. Imagine the universe is a vast sheet of paper. To get from a point on one side to a point on the other, you would normally have to travel the long way across the surface. But if you could fold that paper, bringing the 2 points into alignment and then puncture it with a pencil, you could create a tunnel, a shortcut connecting 2 vastly distant regions of space and time. This isn't a tunnel in the conventional sense. You wouldn't be travelling through the intervening space. You would be exiting space altogether, stepping through a doorway in reality itself to emerge somewhere else, perhaps thousands or even millions of light years away in an instant. It is the ultimate cosmic shortcut. A bridge across infinity. An Einstein-Rosen Bridge, as it was first called, would be humanity's definitive escape from the prison of light speed. The journey of 100,000 years could become a journey of a single step. The stars, once relegated to the realm of myth and distant observation, would become our neighbours. A galactic civilization connected by a web of these cosmic subways could flourish. It is a dream of almost unimaginable power and promise, yet for decades it has remained just that, a dream. A mathematical curiosity confined to the chalkboards of theoretical physicists and the pages of science fiction. The hurdles seemed insurmountable, the physics impossibly exotic. Early models showed that these cosmic tunnels would be catastrophically unstable. A wormhole would snap shut the instant it formed, pinching off into a singularity so quickly that not even a single photon, let alone a spaceship, could make it through. To keep the throat of the wormhole open, to prop it up against the crushing tendency of space-time to smooth itself out, would require something extraordinary. Something that, as far as we know, may not even exist. It would require a substance with properties that defy our everyday experience, a material that possesses negative mass and negative pressure. Physicists call it exotic matter. This isn't just a new type of particle. It's a form of anti-gravity, a substance that would push space-time apart rather than pulling it together. A handful of this material, if you could hold it, would weigh less than nothing. It would actively repel the ground beneath you. To build a stable, traversable wormhole, we would need vast quantities of this phantom material, arranged with impossible precision to act as a celestial scaffold, holding open the gateway to the stars. The search for exotic matter has yielded nothing. The universe we observe seems to be governed exclusively by positive mass and energy. Wormholes, therefore, appeared to be a beautiful but failed promise, a footnote in the grand story of physics. They were a path the universe could have taken, but for which it seemingly lacked the necessary ingredients. The dream of the shortcut was relegated back to the realm of fantasy. We were once again confined to our cosmic island, the walls of our space-time prison standing as tall and as firm as ever. Our destiny, it seemed, was to crawl, not to leap across the heavens. But what if we have been looking in the wrong places? What if the conditions necessary to forge such an extraordinary structure do not exist in the placid, quiet corners of the galaxy, but can only be found in the most extreme, most violent, and most mysterious environment the universe has to offer? What if the key to this impossible dream lies locked away within the very heart of a monster? To find it, we must undertake a journey of our own. Not through a wormhole, but through the power of our telescopes and our imagination. We must travel 26,000 light-years, plunging toward the core of our own Milky Way, past billowing clouds of nascent stars through dense clusters of ancient suns. We push deeper into the galactic centre. The starlight here becomes a torrential flood, the density of stars increasing 1,000,000-fold. It is a brilliant, dazzling and lethal metropolis, a city of 100 billion suns roaring with gravitational and radioactive fury. And at the absolute centre of it all there is a void, a point of perfect darkness, a gaping maw in the star-dusted fabric of the galaxy. This is the lair of the beast, Sagittarius A, our galaxy's supermassive black hole. It is a creature of pure gravity, an object so dense and so powerful that it has fundamentally broken the reality around it. 4,000,000 times the mass of our own sun crushed down into a single point of infinite density, a singularity. It is a gravitational monarch holding the entire galaxy in its thrall. Every star you see in the night sky, including our own sun, is locked in a slow 200-million-year orbit around this single invisible point. Surrounding this point of no return is the event horizon, a spherical boundary of profound consequence. It is not a physical surface, but a demarcation line in space-time. Cross it, and there is no coming back. The gravitational pull becomes so absolute that even light, the fastest thing in the universe, is captured and consumed. It is the edge of the known universe, the place where our laws of physics scream and then fall silent. The environment around Sagittarius A is a maelstrom of cosmic violence, a superheated swirling disk of gas dust, and the shredded remains of unfortunate stars spirals into the abyss, accelerating to near the speed of light. This accretion disk glows with the brilliance of a billion suns, unleashing torrents of X-rays and gamma rays that sterilize the surrounding space. Stars are flung about like stones in a slingshot, some whipped into blisteringly fast chaotic orbits that bring them terrifyingly close to the event horizon before they are hurled back out into the galaxy. We have witnessed clouds of gas larger than our entire solar system stretched and torn apart by the black hole's tidal forces, a process gruesomely nicknamed spaghettification before being devoured. This is no place for gentle physics. This is a cosmic crucible, a gravitational forge where the fundamental rules of space-time are tested to their breaking point. It is a place of endings, a one-way drain in the bathtub of the cosmos, the ultimate symbol of destruction and finality. And yet, it is here in this heart of darkness, amidst this relentless chaos, that something altogether unexpected has been found. For years, astronomers have painstakingly tracked the intricate dance of matter and light around Sagittarius A. They use the world's most powerful telescopes peering through veils of interstellar dust to chart the orbits of stars and the flow of gas, hoping to better understand the nature of this gravitational behemoth. Using these observations, we can build a precise map of the gravitational field, a picture of how space-time is warped and bent in the black hole's immediate vicinity. Our models, based on Einstein's relativity, have been stunningly successful at predicting this complex celestial ballet. They work perfectly. Almost. In the furthest reaches of the data, in the faintest whispers of the gravitational signal, a subtle anomaly has begun to emerge. A tremor. A gravitational signature that does not quite fit. The orbits of some of the most distant objects seem to be affected by a presence, a gravitational influence that the 4 million solar mass black hole alone cannot explain. It is as if something else is there, hiding in the glare and the gravity subtly perturbing the system. It is not a large deviation, nothing obvious or dramatic. It is a ghost in the data, a faint harmonic discord in an otherwise perfect symphony. Scientists have tried to explain it away. Perhaps it is a cluster of smaller black holes or a concentration of exotic dark matter. But none of these conventional explanations perfectly matches the strange signal. A far more radical, far more profound possibility, however, does. An idea once dismissed as pure fantasy has been resurrected not by theorists on a chalkboard, but by the perplexing evidence gathered from the galactic core. The strange gravitational influence, the subtle warping of space-time, is consistent with the presence of a wormhole's mouth. Could the most destructive object in our galaxy be hiding the entrance to the ultimate cosmic shortcut? Is it possible that the extreme warping of space-time caused by a supermassive black hole is precisely the environment needed to naturally stabilize such an exotic structure? The very thought borders on heresy, challenging our deepest assumptions about black holes as points of no return. It suggests that Sagittarius A might not just be a drain, but also a door. A gateway not to oblivion, but to somewhere else entirely. A place across the universe, or perhaps even a different universe altogether. We stand at a precipice of discovery, staring into the abyss at the centre of our galaxy, and finding not just an end, but the tantalizing hint of a new beginning. The age-old dream of the journey of a path to the stars may have been hiding in the last place we ever thought to look. The question that will drive our search is no longer purely theoretical. It is a question for observers, for astronomers, for all of us. What exactly is lurking in the dark heart of the Milky Way? What if the most fundamental anchor of our existence, the very heart of our own galaxy, is not a gateway to oblivion, but a portal to somewhere else entirely? For a century we believed we knew the answer. We gave it a name, a mass, a theory. We even took its picture. But science is not about belief. It is the systematic process of doubt. And at the centre of the Milky Way, a new and profound doubt is beginning to stir, threatening to unravel everything we thought we knew about the cosmic monster sleeping in our own backyard. Before we can confront that terrifying new possibility, we must first understand the behemoth we thought we knew. We must journey to the place where all the stars of our heavens bow in unison to the court of a gravitational king. Our story begins in a place of unimaginable violence and breathtaking beauty. 26,000 light-years from our quiet solar system lies the galactic centre, a sprawling metropolis of cosmic chaos. Here 1,000,000 stars are crammed into a space just a few light-years across, a celestial swarm buzzing with furious energy. Nebulae of superheated gas glowing in ghostly hues of pink and blue are torn asunder by fierce stellar winds. Massive young blue stars, celestial blowtorches living fast and dying, young detonate in cataclysmic supernova enriching the interstellar medium with the heavy elements that make worlds like ours possible. It is a maelstrom of creation and destruction, a place so dense with radiation and obscured by impenetrable curtains of dust that for most of human history its true nature was a complete mystery. We could feel its presence, a gravitational heartbeat guiding our sun on its 250,000,000-year orbit, but we could not see the source. Something was there. Something immense, dark and unimaginably powerful, holding our entire galaxy of 400 billion stars in a gentle gravitational embrace. For decades, this was the ultimate astronomical puzzle. How do you find an object whose defining characteristic is its ability to swallow light itself? The answer, as it so often is in science, was one of patience and profound ingenuity. You don't look for the object. You look for its shadow, for the wake it leaves in the fabric of space-time, for the victims caught in its invisible web. Two teams of astronomers on opposite sides of the globe embarked on one of the longest and most ambitious observational campaigns in history. In Germany, Reinhard Genzel and his team at the Max Planck Institute used the European Southern Observatory's Very Large Telescope in Chile, a quartet of colossal mirrors nestled in the arid Atacama Desert. In the United States, Andrea Ghez and her group at UCLA pointed the twin eyes of the W.M. Keck Observatory perched atop the dormant volcano of Mauna Kea in Hawaii toward the same enigmatic point in the sky. For nearly 3 decades, night after night, they stared into the heart of the Milky Way. They weren't looking for darkness. They were tracking tiny pinpricks of light, a small cluster of stars now famously known as the stars, orbiting what appeared to be absolutely nothing. Their mission was to play a cosmic game of connect the dots, plotting the precise position of these stars year after year. It was a task of maddening difficulty. They were peering through 26,000 light-years of obscuring dust and gas, trying to measure movements smaller than the width of a human hair seen from hundreds of miles away. Our own planet's atmosphere, the turbulent ocean of air we breathe, constantly distorts and blurs the light from these distant suns, making them twinkle and dance uncontrollably. To overcome this, both teams pioneered the use of a revolutionary technology called adaptive optics. It is a marvel of engineering, a system of lasers and deformable mirrors that measures the atmospheric distortion in real time and then corrects for it hundreds of times per second, effectively cancelling out the twinkle. For the first time, the view from Earth became as clear as if the telescope were in space, and the galactic centre snapped into razor-sharp focus. With this newfound clarity, the celestial dance began to reveal its secrets. Of all the S-stars, one became the key witness S2. It was their celestial informant. Over the years, Genzel and Ghez and their teams watched S2 perform a dramatic high-speed gravitational waltz. Its orbit was a highly elongated ellipse, a cosmic slingshot that brought it terrifyingly close to the unseen central object. As it approached its closest point, a point known as periastron, the star's velocity became truly mind-boggling, accelerating to over 7,000 kilometers per second, nearly 3% of the speed of light. It was moving so fast that you could detect its motion not just over months or years, but in a single night of observation. Imagine the gravitational forces required to whip a star of that size to such an incredible speed, and then fling it back out into a quarter-century-long orbit only to have it return again and again with clockwork precision. The laws of celestial mechanics, first penned by Johannes Kepler 400 years ago, are unforgiving. To have an orbit, you must have a central mass. By meticulously tracing the complete orbit of S2 and cross-referencing it with the other S-stars, the teams could calculate the exact mass of the mysterious object they were all dancing around. The number they arrived at was staggering almost beyond comprehension. The invisible object at the centre of this cosmic ballet contained the mass of 4.3 million suns, 4 million stars like our own crushed down into a single point, and all of that mass, according to the tightly constrained orbits, had to be confined within a region of space smaller than the orbit of Mercury. There is only one object in the known universe that can be that massive and that compact. The evidence was irrefutable, the conclusion inescapable. After decades of painstaking work, humanity had finally come face to face with the ghost in the machine, the dark heart of our galaxy. They had proven beyond any reasonable doubt the existence of a supermassive black hole. For this monumental discovery, which confirmed one of the most extreme predictions of Einstein's theory of relativity, Ginzel and Ghez were jointly awarded the Nobel Prize in Physics. They had given a name and a weight to the darkness. They called it Sagittarius A, or Esca A for short. But what is a black hole? The term itself conjures images of cosmic vacuum cleaners of voracious monsters devouring everything in sight. The reality is both simpler and far more profound. It is not an object in the traditional sense, but a location. It is a place where gravity has become so overwhelmingly powerful that it has fundamentally broken the reality we know. The story begins, as it so often does, with Albert Einstein. His general theory of relativity revealed that gravity is not a force pulling objects together, but a curvature in the very fabric of the universe, a four-dimensional tapestry we call space-time. Massive objects like our Sun create a gentle depression in this fabric, and planets like Earth follow the resulting curves like marbles rolling around a bowling ball on a stretched rubber sheet. A black hole is what happens when you take that analogy to its most extreme and violent conclusion. It is a place where matter has been so compressed that its density becomes infinite, carving an impossibly deep bottomless well in the fabric of space-time. This point of infinite density is called a singularity. Here at this single dimensionless point, our laws of physics, of space, of time, of causality simply cease to have any meaning. It is the end of the line for physics as we understand it. Surrounding this unknowable singularity is the feature that gives a black hole its name, the event horizon. This is not a physical surface you could touch. It is an informational boundary, a one-way door in the universe. It is the precise distance from the singularity where the gravitational pull becomes so immense that the escape velocity exceeds the speed of light. Since nothing in the universe can travel faster than light, anything that crosses this threshold, be it a star, a planet, a particle, or a beam of light itself, is trapped forever. It is the ultimate point of no return. For a black hole with a mass of Sagittarius A, this boundary, known as the Schwarzschild radius, is about 12 million kilometers from the singularity, a sphere just 17 times wider than our Sun. Yet within that relatively small volume resides the gravitational authority to command an entire galaxy. Anything that drifts too close, a cloud of interstellar gas or an unlucky star, is ensnared. As it's pulled in, it is subjected to unimaginable tidal forces, a process gruesomely termed spaghettification, where it is stretched and shredded into a stream of superheated plasma. This plasma forms a swirling incandescent accretion disk around the event horizon, a final brilliant scream before being consumed by the silence within. The effects of this gravitational well extend far beyond its immediate vicinity. Space-time is so warped around Esca A that it acts like a cosmic lens. Light from stars positioned directly behind the black hole is bent around its edges, allowing us to see things that should be hidden from view. This phenomenon, known as gravitational lensing, is a direct observable confirmation of Einstein's predictions. Time itself is also a victim of this extreme gravity. For an observer falling towards the event horizon, their clock would tick slower and slower relative to someone watching from a safe distance. To the outside observer, the falling person would appear to freeze at the edge of the abyss, their image red-shifted into oblivion over an infinite amount of time, never quite crossing the threshold. For the person falling in, however, their passage across the event horizon would be instantaneous, a seamless transition from our universe into a future that is singular and inescapable. These are not science fiction concepts. They are the bizarre yet mathematically proven consequences of nature's most extreme gravitational engine. For decades, this was the accepted portrait of Sagittarius A, a magnificent, terrifying, but ultimately predictable consequence of gravity. A monster, yes, but a monster whose behavior we understood. Then humanity decided it was time to take a picture. Proving a black hole exists by watching the stars that orbit it is one thing. To actually see its silhouette would be another thing entirely. It would be like trying to photograph a dark marble against a black background from thousands of light years away. The challenge was immense. SGRA's event horizon, though massive, is so distant that its apparent size in our sky is minuscule equivalent to trying to see a donut left on the surface of the moon. No single telescope on Earth was powerful enough to resolve such a tiny feature, so scientists at the Event Horizon Telescope collaboration came up with an audacious solution. If you can't build a big enough telescope, why not turn the entire Earth into one? Using a technique called very long baseline interferometry, they synchronized a global network of radio telescopes from the mountains of Hawaii to the deserts of Chile, from the plains of Spain to the ice of the South Pole. Each telescope recorded the faint radio waves emanating from the glowing gas around Sagittarius, timed with fantastically precise atomic clocks. The sheer scale of the undertaking was breathtaking. Petabytes of data, more information than is stored in the entire Library of Congress, were recorded onto hundreds of hard drives at each site. Since the data volume was too large to transmit over the internet, these drives were physically flown by airplane to central supercomputing hubs in Germany and the United States. There, a team of brilliant scientists and software engineers led by computer scientist Katie Booman developed new algorithms to stitch this planetary-scale data set together. They had to account for the rotation of the Earth, the wobble in its axis, the interference from our own atmosphere, and the faintness of the signal. After years of painstaking work, they accomplished the impossible. They processed the data and rendered the very first direct image of a black hole's shadow. It was not the crisp, sharp ring of science fiction, but a fuzzy asymmetric glowing donut of orange and black. And it was one of the most beautiful and important images ever captured. The bright ring was not the accretion disk itself, but the light from that superheated gas, lensed and distorted by the black hole's gravity. The dark central region was not the singularity, but the shadow the event horizon casts upon that glowing backdrop. It was the photon capture sphere, a region of empty space where light is forced into unstable orbits, a final fleeting halo before the plunge. The brighter region of the ring told us which way the gas was spinning. The part moving toward us was brightened by relativistic beaming, while the part moving away was dimmed. The image was a stunning confirmation of everything we predicted. The size and shape of the shadow perfectly matched the predictions of Einstein's theory for a black hole of 4 million solar masses, the decades of watching the S-stars, the complex theories of General Relativity, and the planet-spanning technological achievement of the Event Horizon Telescope had all converged on this single spectacular image. The case seemed closed. Sagittarius A was precisely the object we thought it was, a perfectly ordinary, if colossal, supermassive black hole abiding by all the known laws of physics. We had stared into the abyss, and the abyss stared back with a face we recognized. For all its monumental clarity, however, a shadow can hide many things. Science progresses not when theories are confirmed, but when they are broken by an anomaly, a tiny crack in the edifice of our understanding. The portrait of Sagittarius A, so carefully painted over decades of observation and theory, appeared complete. It was a masterpiece of human intellect and curiosity, a testament to our ability to comprehend the cosmos. But in the mountain of data from the Event Horizon Telescope, and in new, more precise measurements of the stars that orbit it, a whisper was beginning to emerge. A subtle deviation, a signal in the noise that didn't quite fit the perfect, elegant model we had just so proudly constructed. The gravitational king at the centre of our galaxy, so long thought to be a predictable, stable monarch, might be harbouring a secret of its own. A secret that would challenge the very nature of space-time and reality itself. The long, comfortable silence of our understanding was about to be shattered. For a century, our portrait of Sagittarius A has been one of sublime, terrifying simplicity. A gravitational monolith governed by laws so pure, so absolute they could be written on a postcard. We saw it as the perfect predator, its behaviour dictated solely by the elegant equations of Einstein. Every star captured in its gravitational embrace, every wisp of gas spiralling to its doom, seemed to confirm this picture of clockwork certainty, a masterpiece of cosmic predictability. You could in theory calculate its every move for 1 billion years. But perfection in the cosmos is a fragile illusion. It is often just a mask for our own ignorance, a placeholder for a deeper, stranger reality. And as our instruments grew sharper, our gaze more persistent, we began to see cracks appearing in that perfect portrait of our galaxy's heart. Subtle inconsistencies, quiet whispers of dissent from the celestial choir. We started noticing things that, according to the simple model, simply should not be there. The first clue came from the silent, frantic dance of the S-stars. These are the suns shackled to Sagittarius A, condemned to execute the tightest, fastest orbits we have ever witnessed anywhere in the universe. For decades we've tracked them, using their motion as golden proof for the black hole's existence and mass. Their loyalty to the laws of gravity seemed absolute, until we focused on one star in particular, an object known to us as S62. It follows a path so daringly close to the abyss that its entire orbit completes in less than a decade. According to our models, its trajectory should be a clean, predictable ellipse, albeit one that wobbles or precesses in the warped space-time near the black hole's edge. This is a well-understood artifact of general relativity, a gravitational waltz we expect to see. But the waltz performed by S62 is off-key. There's an extra shimmy in its motion, a minute, almost imperceptible deviation from its predicted path. It's a tiny hiccup in its celestial choreography, so small that for years it was dismissed as observational noise, a smudge on the lens. But the signal refused to disappear. With every passing year, the deviation grew, confirming itself as a real physical phenomenon. The star was being nudged by something other than the colossal gravity of Sagittarius A. It's a familiar story in the history of astronomy. In the 19th century, astronomers noticed that the planet Uranus was straying from its calculated orbit. It was being pulled by an unseen hand, a gravitational ghost. That ghost, when they finally tracked it down, turned out to be the planet Neptune, an entire world discovered not by sight, but by its subtle, gravitational whisper. So what is whispering to S62? What unseen Neptune is tugging at this star from the edge of oblivion? The most obvious answer would be another black hole, a smaller companion orbiting the supermassive primary. We have searched for it. We have scoured the galactic center with our most powerful telescopes, looking for the telltale radiation, the gravitational tremors of a second object. The search has come up empty. There appears to be nothing there massive enough to account for the star's peculiar dance. The gravitational ghost remains stubbornly invisible, leaving us with a disturbing puzzle. The math is precise. The observation is clear. The simple explanation is missing. The mystery only deepened when our radio telescopes, tuned to the cacophony of the galactic core, picked up another anomaly, something entirely different. We are accustomed to the violent outbursts from Sagittarius A. As matter is torn apart in the accretion disk, it screams in high-energy X-rays and furious radio flares. These are the death cries of stars and gas clouds, chaotic, unpredictable, and raw. But this new signal was none of those things. It was quiet, eerily regular. It appeared as a faint pulse of low-frequency radio waves repeating with the precision of a metronome. Once every 76 minutes, a soft rhythmic beat emerged from the background noise. This celestial heartbeat was profoundly unnatural. Chaos is the rule in the environment of a supermassive black hole. Order, especially clockwork regularity, is the exception, and it demands an explanation. What could possibly produce such a steady pulse from the most violent region in our galaxy? It couldn't be a pulsar. The black hole's immense gravity would have torn it to shreds, or ejected it long ago. It didn't match the signature of any known stellar object. Stranger still was its apparent location. Triangulating the signal, our astronomers traced it back to a point in space, seemingly empty, a region just outside the event horizon, where there should be nothing but vacant, twisted space-time. It was a lighthouse beacon shining from a phantom island, a rhythmic whisper from an empty room, a signal with no apparent source broadcasting its perfect timing into the void. And then came the most baffling discovery of all, a discovery born not from light, but from the trembling of space-time itself. For the past decade, we have been gifted with a new sense. We can now feel the vibrations of the universe, the gravitational waves produced by the most cataclysmic events. When two black holes collide, they send ripples through the fabric of reality, a cosmic chime that travels for billions of years to reach our detectors on Earth. Some time ago, our observatories detected such a merger, a colossal collision in a distant galaxy. We recorded the signal a characteristic chirp that told us the story of two giants becoming one. It was a spectacular but by now routine observation. The story should have ended there, but it didn't. A few minutes after the primary signal had faded, our most sensitive instruments picked up something else. A faint distorted echo of the exact same event. It was the same gravitational wave chirp, the same cosmic story, but it was weaker warped, and it arrived inexplicably late. Our global network of detectors confirmed the finding. This was no instrument glitch, and when we traced the direction of this ghostly echo, our calculations pointed to an impossible origin. The echo seemed to have come from the direction of our own galactic centre, from Sagittarius A. How could this be? How could a gravitational wave from a distant galaxy arrive at Earth, only to be followed by its own echo from a completely different point in the sky? It was as if you shouted into a valley and heard your echo return not from the cliff face in front of you, but from the ground beneath your feet. The signal had somehow been rerouted. It implied that the wave had travelled to our galactic centre and then been reflected back to us. But black holes don't reflect gravitational waves. They are the ultimate cosmic sinks. Anything that enters, including the curvature of space-time itself, never leaves. To generate such an echo would require something other than a black hole. It would require a structure in space-time that we have only ever dreamed of. Something that could capture a wave and then release it. Something that could create a cosmic shortcut. These anomalies, the star that dances to an unseen rhythm, the heartbeat from an empty void, the impossible echo of a distant cataclysm, they force us to confront a radical possibility. They are pushing us past the known boundaries of physics, urging us to ask a question that sounds like science fiction. What if Sagittarius A is not just an endpoint? What if the perfect portrait of a simple black hole is incomplete because it's missing a fundamental feature? What if our galaxy's supermassive heart is also a gateway? To understand this staggering idea, we must journey back to the very roots of Einstein's theory, back to a ghost that has haunted the mathematics of relativity for over a century. When Albert Einstein and Nathan Rosen first explored the bizarre geometry of a black hole, their equations presented them with a startling duality. For every solution that described a black hole, a region of space you could enter, but never leave, the mathematics also described its perfect opposite, a white hole, a region you could leave but never enter. The equations seemed to suggest that these two phenomena were fundamentally linked. They weren't just separate oddities, they were two sides of the same coin, two mouths of a single extraordinary tunnel through the fabric of space-time. This theoretical connection, this shortcut through the cosmos, was named the Einstein-Rosen Bridge. To us it is better known by a far more evocative name, a wormhole. Imagine space-time not as a flat, infinite expanse, but as a vast sheet of paper. To get from one point to another, you would normally have to travel across the surface. A wormhole is what happens when you bend that paper, folding the universe over on itself, and punch a hole straight through, connecting two distant points with a breathtakingly short tunnel. A journey that might take 100,000 years travelling at the speed of light could be traversed in mere moments. It was a stunning, almost magical prediction born from the cold, hard logic of mathematics. A doorway to the stars hidden within the machinery of the universe. But there was a devastating catch. The Einstein-Rosen Bridge, this primordial wormhole, was a cosmic mirage. The mathematics showed that it was profoundly unstable. The tunnel wasn't a static corridor. It was a dynamic, fleeting event. It would pinch off and vanish with such incredible speed that not even a single photon of light, the fastest thing in the universe, would have time to make it from one side to the other. Trying to cross an Einstein-Rosen bridge would be like trying to leap through a doorway that slams shut 1 billion times faster than you can blink. It was a path that existed only in theory, a tantalizing glimpse of a possibility that nature seemed to forbid. For decades, the wormhole remained a mere curiosity, a piece of mathematical graffiti on the walls of physics, a beautiful but ultimately useless idea. But science rarely lets a beautiful idea die. Throughout the 20th century, physicists driven by a blend of rigorous calculation and boundless imagination kept returning to the puzzle. If the natural wormhole was impassable, Could an artificial one be constructed? Could a sufficiently advanced civilization find a way to prop the door open? The quest to answer this question led to one of the most bizarre and challenging concepts in all of physics. The problem with the wormhole is that gravity by its very nature wants to crush the tunnel shut. Space-time itself wants to collapse the bridge. To counteract this, you would need to line the throat of the wormhole with something that fights back. You would need a form of anti-gravity. This is not the stuff of fantasy spaceships. It is a specific theoretical requirement known as exotic matter. To keep the tunnel open to create a truly traversable wormhole, you would need a substance that has negative energy density. Imagine a ball that instead of having weight has anti-weight. If you put it on a scale, the scale would read less than 0. Gravity, instead of pulling on it, would push it away. This is the kind of mind-bending material needed to act as a cosmic scaffold, prying open the wormhole and holding it stable against the relentless crush of space-time. For a long time, such a thing was thought to be utterly impossible, a violation of the known laws of energy. It seemed to be the final nail in the coffin of interstellar travel through cosmic tunnels. But then a strange light appeared from the murky depths of quantum mechanics. The quantum world is a place of profound uncertainty, where particles pop in and out of existence from nothing, and where the very concept of empty space is a seething foam of virtual energy. Within this quantum foam, theorists discovered it was possible for localized pockets of negative energy to exist, if only for fleeting moments. The Casimir effect, a phenomenon now experimentally verified, shows that two closely spaced metal plates in a vacuum will be pushed together by a subtle, negative energy pressure. It's a tiny microscopic hint from nature. A whisper that the seemingly impossible building blocks for a wormhole might not be forbidden after all. We have no idea how to gather this exotic matter, how to stabilize it, or how to build anything with it. But its theoretical possibility keeps the dream alive, the dream of a stable, traversable wormhole, a permanent bridge across the cosmos, and this brings us back to the heart of our own galaxy. Back to the anomalies plaguing Sagittarius A. If by some mechanism, either natural or engineered by an intelligence beyond our comprehension, a traversable wormhole were connected to our supermassive black hole, what would we expect to see? What signatures would this cosmic gateway leave behind for us to find? Suddenly, the pieces of the puzzle begin to snap into a coherent though unbelievable picture. Consider the wobbling orbit of the star S62. A wormhole, even one with no mass passing through it, is a profound distortion of space-time geometry. Its mouth would exert its own subtle yet persistent gravitational influence. It would behave like an invisible mass, a gravitational ghost, tugging on anything that passed too close. It would create the precise kind of small, unaccounted-for perturbation that we observe in S62's orbit. The unseen Neptune we've been hunting for might not be a planet or a star at all. It could be the entrance to another place or another time. Then there is the mysterious rhythmic radio pulse, the heartbeat from the void. If the wormhole connects our region of space to another, it is a two-way street. Energy and matter could potentially leak through. That faint, perfectly regular signal coming from a place where nothing should be could be the signature of something on the other side. A pulsar, perhaps, in a distant galaxy, its regular beam shining down the tunnel, its light arriving in our sky from a phantom source. The beacon isn't on a phantom island. It's shining from across a cosmic ocean through a tunnel drilled through the heart of our galaxy. And finally, there is the most compelling clue of all the gravitational wave echo. A wormhole is the ultimate cosmic shortcut. Imagine the original wave from that distant black hole merger spreading out across the universe. Most of it travels the long way through normal space-time, eventually reaching our detectors. But a portion of that wave by chance enters the distant mouth of a wormhole, travels instantaneously through the tunnel, and exits near Sagittarius A. From there, it travels the short remaining distance to Earth. This would create exactly what we saw: a primary signal that took the scenic route, and a fainter, slightly distorted echo that took the express lane. The wormhole doesn't reflect the wave. It provides an alternate path, a secret passage through the universe. It is the only known theoretical structure that could possibly account for such a phenomenon. The theory is outlandish. The implications are staggering, yet the evidence, however circumstantial, refuses to be ignored. Each anomaly taken alone could perhaps be dismissed or explained away with a more conventional theory, but taken together they paint a startlingly consistent picture. They all point in the same direction toward the same unbelievable conclusion. We came to the galactic centre looking for a simple monster, a perfect singularity of predictable physics. We may have found something infinitely more complex and infinitely more profound, a nexus, a crossroads. The observations are tantalizing, the theoretical framework is in place, but we are standing at the edge of the greatest scientific precipice in human history. We have a ghost story supported by whispers and shadows. Now we face the monumental task of proving it. How do we move from these subtle hints to undeniable proof? How do we distinguish a glitch in the data from a gateway to the stars? The answer will require a new generation of instruments and a boldness of thought that dares to confront the truly fantastic. The hunt is on. And so after decades of patient observation, the celestial ballet around Sagittarius A had become almost familiar, its violent choreography mapped with breathtaking precision. We had grown accustomed to the S-stars, those high-velocity trailblazers, as they swung perilously close to the maw of the abyss, their orbits a testament to the raw, unyielding power of a 4 million solar mass singularity. Each star was a known quantity, a character in a gravitational drama whose script we thought we had finally deciphered. But the universe, it seems, rarely sticks to the script we write for it. The next chapter in this story wouldn't begin with a grand explosion or a brilliant flash, but with a whisper. It began with an anomaly, a single data point that refused to conform, a celestial actor that had missed its cue. It began in the sterile, data-saturated halls of the Max Planck Institute for Extraterrestrial Physics, with a small, dedicated team who called themselves the Odyssey Group. For them, the galactic centre was not a distant abstraction. It was a living laboratory, a place they visited every night through the cold, unblinking eyes of the world's most powerful telescopes. Leading them was Dr. Aris Thorne, a man whose quiet demeanour concealed a relentless, almost obsessive focus. For years, his team had been engaged in the painstaking work of identifying new fainter S-stars, pushing the limits of technology to find ever more intimate witnesses to the supermassive black hole's domain. Their work was a form of cosmic archaeology, sifting through mountains of photometric data and spectroscopic signals looking for the telltale Doppler shift of a star caught in an extreme gravitational dance. Most of their discoveries were confirmations adding new points of light to an already established map, reinforcing the beautiful, predictable clockwork of General Relativity. But in the early winter of 2028, amidst the terabytes of information gathered by the gravity instrument on the Very Large Telescope Interferometer, something new appeared. A faint, previously uncatalogued star designated S108 was making its first observed pericenter passage, its closest approach to the black hole. And it was behaving impossibly. At first, the anomaly was subtle enough to be dismissed as instrumental noise, a glitch in the sophisticated network of lasers and mirrors that allowed them to achieve such astounding resolution. A star moving at nearly 3%, the speed of light doesn't just travel in a smooth, perfect ellipse. Its orbit is a precessing rosette, a beautiful, swirling pattern, predicted by Einstein himself, where the point of closest approach shifts with every revolution. This gravitational waltz was the expected signature, the rhythm they knew by heart. S108, however, seemed to add its own bizarre, unscheduled flourish to the dance. As it plunged toward the black hole, accelerating to unimaginable speeds, its trajectory registered a tiny, almost imperceptible deviation. It was a flinch, a gravitational stutter. For a fraction of a second, the star's path wobbled as if it had momentarily encountered a pocket of space-time that was denser, or perhaps fundamentally different from its surroundings. It was as if a marble rolling across a perfectly smooth sheet of rubber had hit an invisible microscopic bump, deflecting it ever so slightly before it continued on its way. Thorne's team spent the next 3 months in a state of controlled panic, trying to kill their own discovery. Science demands skepticism, and extraordinary claims require the most rigorous self-assault. Their first assumption was simple error. They recalibrated their instruments from afar, triple-checked every line of code in their analysis software, and had their data independently reviewed by colleagues who knew nothing of the anomaly. The stutter remained. It was real, embedded in the photons that had travelled 26,000 years to reach their detectors. Their next line of attack was to find a conventional explanation. The region around Sagittarius A is not empty. Perhaps an unseen object, a smaller intermediate mass black hole or a compact star cluster had passed by S108 at that precise moment, giving it a slight gravitational kick. They ran hundreds of simulations populating the digital space around the black hole with every conceivable object. But nothing worked. To produce a kick sharp enough to match the data, the unseen object would have to be incredibly massive and incredibly compact, and its passage would have to be timed with a coincidence that bordered on the miraculous. Furthermore, such an object should have revealed its presence by its effect on the other S-stars, but their orbits remained pristine, undisturbed. The disturbance was hyperlocalized, a phantom effect that touched S108 and S108 alone. Frustration mounted. The answer, whatever it was hiding from them. Thorne, feeling the immense pressure of the anomaly, turned to another aspect of the data that had been nagging him: gravitational lensing. As S108 began its journey away from the black hole, its path took it almost directly behind the central mass from our point of view on Earth. The light from the star as it passed through the deeply warped space-time around Sagittarius A should have been bent into a predictable shimmering arc, a classic Einstein ring. The team's instruments were designed to capture precisely this effect, to see the way the black hole's gravity acts as a cosmic magnifying glass. They had seen it before with other stars, a clean, elegant distortion that matched the predictions of relativity to the 99th decimal place. But the light from S108 was different. It wasn't a clean arc. As the star slipped behind the zone of influence, its lensed image did something utterly baffling. It split. For a few precious hours, the Very Large Telescope didn't see one lensed image of S108, but two. Two faint, ghostly copies of the star appeared separated by a tiny yet measurable angle. One image was slightly brighter, arriving a few minutes before the other. It was a temporal echo, a ghost in the machine of gravity. This was not the signature of a simple solid object. A standard black hole, no matter how massive is a singularity of gravity, it has one center. It should produce one primary lensed image. To create two, the light from S108 must have been presented with a choice. It must have travelled along two distinct paths of different length through the gravitational field, arriving at our telescopes as two separate signals. The implications were staggering, bordering on scientific heresy. What kind of object could possibly offer two different routes for light to travel around it? What sort of gravitational topology could create such a schism in reality? The atmosphere in the lab shifted from frustration to a kind of terrified awe. The team had been looking for a misplaced object, a stray black hole or a dense cluster. But the data was no longer pointing to an object in space-time. It was pointing to a change in the nature of space-time itself. It was Thorne who finally dared to voice the thought late one night in the echoing silence of the computer lab, surrounded by glowing screens that all told the same impossible story. He pulled up a series of theoretical models that had been relegated to the fringes of physics papers discussed more often in science fiction than in serious academic circles. These were the metrics for what physicists call non-trivial topologies, solutions to Einstein's equations that permit shortcuts, bridges and tunnels through the cosmic fabric. He keyed in the parameters for a traversable wormhole, a stable microscopic throat connecting our region of space-time to another, either a different location in our own universe, or somewhere else entirely. It was a wild, desperate guess, an act of intellectual abandon. He ran the simulation. The digital model of S108 was set on its course not towards a simple point-like singularity, but towards a black hole with a tiny traversable mouth embedded near its event horizon. As the simulated star approached its pericenter, the complex tidal forces from the wormhole's opening exerted a subtle fleeting pull. On the screen, the star's orbit registered a tiny deviation, a flinch, a gravitational stutter. Thorne felt a cold shiver run down his spine. The simulated wobble was a near-perfect match for the real-world data. His heart pounded in his chest as he let the simulation continue, tracking the starlight as it passed behind this exotic object. The program calculated the paths the photons would take, Some would travel through the warped space around the black hole's side, but others, a small fraction, would be diverted through the very edge of the wormhole's gravitational influence, a slightly different path with a different length. The result when viewed from a simulated Earth was not one lensed image but two, a primary image and a fainter, slightly delayed echo. Just like the ghost they had seen in the sky, it was all there, the stutter, the double lensing. Two independent bizarre phenomena, both explained by a single, terrifyingly elegant and profoundly radical hypothesis. This wasn't proof. The word proof is a sacred one in science, earned through decades of overwhelming corroborating evidence. What they had was a candidate, a single tantalizing thread of evidence pointing towards the most profound discovery in the history of human exploration. They spent another 2 months writing the paper, their every word chosen with surgical precision. They used cautious academic language, referring to the object not as a wormhole, but as a candidate for an exotic compact object with non-trivial topological features. They detailed every painstaking step they had taken to eliminate conventional explanations. They laid out the raw data, the astrometric position of a wobbling star, the photometric readings of a phantom photon echo for the entire world to scrutinize. They knew what was coming. They were about to light a fire. On a cold Tuesday morning in February, they uploaded their paper, Anomalous Astrometric and Photometric Signatures, in the S-Star S108, to the R-Hire, the online preprint server where physicists share their work before formal peer review. Within an hour, the news had begun to spread, first through hushed emails between astrophysics departments, then through frantic posts on academic forums. By noon, it was an explosion. The Odyssey Group's carefully measured paper with its dense equations and dispassionate tone had hit the scientific community with the force of a supernova. It was the moment everything changed. The moment a wild, speculative idea, the dream of science fiction, suddenly had a coordinate on the sky. A specific place you could point a telescope and say, there, something is happening there that should not be possible. The world's astronomers, who had been content to study the predictable physics of a familiar monster, suddenly found their ears perked, their heads turned, their minds racing. They were no longer just looking at a black hole. They were staring into the heart of a mystery that questioned the very continuity of our cosmos, and every observatory on the planet began to pivot slowly, inexorably, towards the dark, silent heart of the Milky Way. The hunt was on. The revelation sent not a ripple but a tidal wave through the world of astrophysics. In the quiet halls of academia and the bustling control rooms of our great observatories, the announcement of a potential wormhole candidate was met with a breathtaking collective silence. A silence followed almost instantly by a deafening roar of inquiry, debate, and profound, unyielding skepticism. For science, especially, a science that deals with the very architecture of reality, does not accept miracles. It interrogates them. The extraordinary claim made by the Event Horizon Telescope Consortium was not a gospel to be believed, but a gauntlet thrown down challenging the entire community to prove it wrong. And so began the trial of the millennium held in the unforgiving cosmic courtroom of peer review. Almost immediately, a firewall of professional caution went up. Every scientist who had ever pointed a telescope at the void, every theorist who had ever wrestled with Einstein's field equations, understood the monumental weight of the claim. To announce a wormhole is to announce a bridge between universes, a shortcut through space-time, a physical manifestation of science fiction's most cherished dream. It is a claim so profound that it risks undermining the credibility of the entire field, if not handled with the most severe intellectual rigor. Careers' reputations and the very integrity of the scientific method were suddenly on the line. The initial euphoria of the Discovery team was now met with the cold, analytical gaze of their peers, a gaze sharpened by decades of debunking false signals and chasing down astrophysical ghosts. The first and most powerful counterargument the leading suspect in this cosmic identity theft was an old and familiar beast, a binary black hole. It was the Occam's razor of the situation, the simplest, most conventional explanation that could potentially account for the bizarre data. The team had observed what looked like a single stable gravitational anomaly, a strangely serene throat of warped space-time. But what if it wasn't a single object at all? What if instead we were witnessing a performance, a celestial illusion, choreographed by two black holes locked in an impossibly tight frantic orbit around each other? Imagine two gravitational titans each, a monster in its own right, spinning around a common centre of gravity. Their combined mass, their intertwined gravitational fields, could potentially mimic the lensing signature of a single, more exotic object. From our distant vantage point, billions of light years away, we wouldn't see two distinct points of darkness. We would see their blended influence on the light from the stars and gas behind them. Their rapid dance would churn the fabric of space-time into a froth, a gravitational gyroscope of immense complexity. This churning, this violent frame dragging, could create a region of such extreme lensing that it might appear from the right angle and with limited resolution as a stable, traversable throat. The light from a distant star passing through this gravitational vortex might be bent in such a way that it seems to emerge from the other side, creating the illusion of a shortcut that isn't actually there. It would be a mirage, a trick of light and gravity, but a convincing one. The proponents of this theory argued that we hadn't found a doorway. We had stumbled upon a cosmic waltz of such speed and intimacy that we had mistaken the dancers for a single impossible entity. To distinguish between the two would require listening for a very specific song. Two black holes orbiting each other are the universe's most powerful gravitational wave emitters. As they spiral closer, they should be screaming into the cosmos, broadcasting their presence in ripples of space-time. The team's initial observations had been primarily electromagnetic, focusing on how the object bent light. But the true test, the smoking gun for the binary hypothesis, would lie in the gravitational spectrum. Our instruments, like the Laser Interferometer Gravitational Wave Observatory, would need to listen for the specific chirp, the rising crescendo, of two massive bodies about to merge. If that signal was detected, the wormhole dream would likely evaporate. But the candidate designated GWC1 sat in a region of space so dense with gravitational noise so close to the thundering heart of Sagittarius A that isolating such a signal would be like trying to hear a single whisper in the midst of a hurricane. The silence from our gravitational wave detectors was for now as ambiguous as the light from our telescopes. While the binary black hole hypothesis represented the conservative vanguard, another more ethereal suspect was proposed by theorists working at the fringes of particle physics. This explanation invoked the greatest mystery of modern cosmology, dark matter. We know this invisible substance is real. We see its gravitational effects everywhere, from the rotation of galaxies to the large-scale structure of the universe. It is the invisible skeleton upon which the visible cosmos is built. But we have no idea what it is. For decades, physicists have theorized about its nature, proposing a menagerie of exotic particles. What if some argued GWC1 wasn't a hole in space-time at all, but rather an unprecedented concentration of it, an ultra-dense, gravitationally compact halo of a strange, undiscovered form of matter? Picture a sphere not of collapsed stars, but of something far more alien. Perhaps a boson star, a theoretical object formed from particles called bosons, which can occupy the same quantum state and pack together with incredible density without generating the heat and pressure of normal matter. Or maybe it was a clump of axions, another hypothetical particle forming a gravitational anchor of immense power. Such an object would be utterly transparent, emitting no light, no radiation, no heat. It would be a ghost in the machine. Yet its gravitational pull would be colossal. It could bend light, warp the paths of stars, and hold its position, with the eerie stability that the Event Horizon team had observed. It would be a perfect gravitational mimic, a celestial doppelganger. This hypothesis was both elegant and deeply frustrating. It explained the observations using a known unknown, the dark matter we know must exist, but it invoked a specific form of it that remains entirely theoretical. How could you prove it? You can't bounce a radio wave off a ghost. You can't detect the heat from an object that has none. The only way to test this idea would be to find subtle, secondary gravitational effects, unique to a massive ball of exotic particles as opposed to a singularity. For instance, a wormhole throat, according to some theories, should have a very specific hard edge to its gravitational field. A diffuse ball of dark matter, even an incredibly dense one might have a softer, more gradual influence on space-time. Discerning this difference from our position peering through the dust and gas of the galactic centre would push our current technology to its absolute limit, demanding a level of precision that is still just beyond our grasp. The dark matter hypothesis hung there a tantalizing and possibly untestable alternative, a shroud of mystery wrapped around an enigma. And then came the theorists who reached even further back, not just across space but across time itself to the very dawn of creation. They proposed a third suspect born in the first chaotic second of the Big Bang, a primordial black hole cluster. Unlike the stellar mass black holes that form from the collapse of giant stars, primordial black holes are thought to have been forged in the immense pressures of the early universe, squeezed into existence from fluctuations in the cosmic plasma. Some theories suggest they could be incredibly small, some no bigger than an atom yet containing the mass of a mountain or an asteroid. They would be scattered throughout the cosmos like ancient dark seeds. For the most part, they would be solitary wanderers too small and isolated to have a significant effect. But what if over the course of 13 billion years, a dense swarm of them had been gravitationally shepherded into one place? What if near the galactic centre, a vast cloud of these microscopic ancient singularities had coalesced into a single massive collective? From a distance, this swarm of gravitational gnats would behave gravitationally as one single supermassive object. The cluster itself could be stable, with the individual black holes orbiting a common centre, their combined gravitational field creating the exact lensing effect that had so captivated the world. It wouldn't be a single throat, but a porous, buzzing hive of countless tiny space-time pits. This hypothesis had a certain poetic appeal, linking a brand new discovery to the very first moments of our universe. Testing this idea presented its own unique set of Herculean challenges. A single wormhole throat should be in theory a relatively clean gravitational environment. A cluster of 1 trillion microscopic black holes, however, would be gravitationally messy. A star passing too close wouldn't just be deflected, it might be subtly jostled and perturbed by the individual members of the swarm. We might be able to detect a faint chaotic flicker in the light of background stars as they are lensed not by one smooth curve, but by a multitude of tiny shifting gravitational wells. This flickering would be a key signature, a telltale sign of the cluster's true nature. But again, detecting such a faint and rapid signal from the galactic core, a region already boiling with energetic activity, would be a monumental feat of observation. It required a new way of looking, a new sensitivity to the universe's most subtle tremors. This is the brutal, beautiful reality of frontier science. For every spectacular claim, the community erects a gauntlet of plausible alternatives. A binary black hole waltz a ghostly sphere of dark matter, a buzzing swarm of primordial relics. Each of these ideas was in its own way less exotic than a wormhole. They stretched our understanding, yes, but they did not fundamentally break it. They operated within the established if incomplete framework of physics. A wormhole, by contrast, required a new physics, a new understanding of gravity, perhaps even the existence of negative energy or extra dimensions. It was the explanation of last resort, the one you only turn to when every other possibility, no matter how strange, has been systematically and definitively ruled out. The core of the problem, the reason for this intense debate, is a concept physicists call degeneracy. It's the idea that wildly different physical systems can, from a distance, produce identical observational signatures. A single massive object can produce the same gravitational lensing as two smaller objects orbiting closely. A hole in space-time can in principle bend light in the same way as a dense ball of invisible matter. We were facing a case of cosmic forgery, where multiple suspects could leave the same gravitational fingerprint at the scene of the crime. The data from the Event Horizon Telescope, revolutionary as it was a single photograph from one angle. It was a stunning clue, but it was not by itself enough to secure a conviction. The scientific community wasn't being difficult or obstinate. It was being disciplined. It was refusing to be seduced by the siren song of the impossible until every mundane port had been explored. The burden of proof, therefore, remained squarely on the shoulders of the Discovery team and their supporters. They had to do more than just show that their data was consistent with a wormhole. They had to demonstrate beyond any reasonable doubt that it was inconsistent with everything else. They needed to find a unique, unambiguous signature, a feature that only a wormhole could possess. Perhaps it was the detection of exotic radiation leaking from the throat, a sign of the negative energy needed to keep it open. Or maybe it was the observation of something truly impossible light from a star known to be on the other side of the galactic centre, somehow shining through this impossible shortcut. That would be the ultimate proof, the observation that would change the course of human history. And so the great debate rages on in journals at conferences and on whiteboards late into the night. The candidate GWC1 sits there at the heart of our galaxy, a silent cosmic sphinx. It poses a riddle not in words but in the language of bent starlight and warped time. Is it a doorway to another place, another time, or is it merely a magnificent illusion, a celestial masquerade put on by more familiar if no less awesome cosmic actors? The answer is not yet known, but the search for it is pushing us to the very edge of what we know and what we can imagine. To break the deadlock, to force the Sphinx to give up its secrets, we would need to go beyond simply looking. We would need to devise a new kind of experiment, a new way of interrogating the void to finally determine if we are staring at a cosmic dead end or into the mouth of infinity itself. The impasse for a time felt absolute. On one side, the colossal phantom of a binary black hole, a gravitational waltz of two invisible titans, its deadly choreography, the most conventional explanation for the bizarre signals rippling from the galactic core. On the other, the ghostly menagerie of theoretical physics quark stars, boson stars, each a desperate attempt to explain the unexplainable, using physics we can only dream of. And then there was the third possibility, the one whispered in conference hallways and sketched on late-night whiteboards, the hypothesis so profound, it felt more like mythology than science. The gateway! For months, the data we had was a cosmic Rorschach test where every team of scientists saw the pattern that best fit their own beliefs. The debate raged not with anger, but with the quiet, intense passion of those who stand at the very edge of a new map, arguing over which direction leads to the sea. To settle it, to force the universe to show its hand, we needed more than just a better telescope. We needed a new way of seeing. We needed a lens the size of a planet. And so we built one. Not from glass and steel, but from a constellation of instruments scattered across the globe from the high arid plains of the Atacama to the frozen heart of Antarctica. The Event Horizon Telescope, a project that had already gifted humanity its first ever glimpse of a black hole silhouette, was being pushed into a new, even more ambitious phase. By synchronizing these disparate observatories with atomic clock precision, we could triangulate on a single point in the heavens, achieving a resolution so fine it would be like seeing an apple on the surface of the moon. This time its gaze would be fixed upon our anomaly, the shimmering question mark hanging in the void, next to Sagittarius A. For 1 week, this planetary eye would stare unblinking into the core gathering not light in the conventional sense, but the faint ghostly hum of radio waves, the echoes of matter being tormented by an immense gravitational field. The raw data that flooded in was not an image. It was a deluge of petabytes, a storm of numbers meaningless to the human eye, a cryptic scripture that held the answer if only we could learn to read it. The first suspect to be placed on this new unforgiving witness stand was the binary black hole. It was the safest, most logical bet. Two smaller black holes locked in a tight decaying orbit could certainly produce the strange gravitational tides and energy flares we had observed. The theory was elegant, it was familiar, and it required no new physics. If this were the case, the Earth-sized eye of our new telescope should see something specific, a telltale wobble, a slight periodic shift in the gravitational centre of the system, the signature of two distinct masses dancing around a common point. The first processed results began to form on screens in labs from MIT to Munich, the petabytes of noise slowly being tamed by supercomputers into a coherent signal. The science team gathered in a state of suspended animation watched as the image resolved. They were looking for the wobble, a dip here, a sway there. But the data was utterly stubbornly monolithically still. The gravitational anchor point of the anomaly was singular. It did not move. It did not oscillate. It was one thing in one place. In a single silent moment of dawning realization, the most plausible theory on the board was not just weakened, it was executed. The celestial dance was a solo. The room, you must imagine, did not erupt in cheers. The death of a leading hypothesis is not a victory, but a deepening of the mystery. It plunges you further into the dark. The next suspect was far more exotic, the boson star. This is an object born not from the collapse of a sun, but from the strange quantum rules that govern a theoretical type of particle, a vast fuzzy ball of concentrated energy that mimics the gravity of a black hole but has no singularity and no event horizon. It's a ghost made of math. Alongside it on the list of phantoms was the quark star, a hypothetical core of a neutron star so compressed that its protons and neutrons have dissolved into a soup of their fundamental components, quarks. Both of these bizarre objects would appear as a single gravitational point consistent with the new data, but they would have one key difference from a true black hole or a wormhole: they have a surface. A strange exotic surface to be sure, but a surface nonetheless. And a surface, no matter how strange, must interact with the tortured plasma swirling around it. It should heat up. It should glow, emitting a specific faint thermal signature in the infrared spectrum, a whisper of heat where a black hole would offer only absolute cold. This was a job for a different kind of eye. We turned to the James Webb Space Telescope, a golden honeycomb adrift in the dark 1,000,000 miles from Earth. Its infrared vision is so sensitive it could detect the body heat of a bumblebee at the distance of the moon. It stared into the anomaly's heart, sifting through the overwhelming glare of the galactic center, hunting for that one specific faint wavelength of light, the thermal ghost of a surface. For weeks the data was collected, cleaned the background noise of 1,000,000,000 other stars meticulously subtracted. The final spectrum that emerged was one of the cleanest, most perfect signals ever captured from the galactic core. It showed the brilliant chaotic light of the accretion disk, the swirling maelstrom of infalling matter. But where the thermal signature of a boson or quark star's surface should have been, there was only a profound and unnerving absence. A flat line. A perfect chilling void of information precisely where the suspects were supposed to be. It was the sound of silence. It was the definitive proof of nothingness. The exotic stars, the last of the reasonable alternatives, were gone, wiped from the board. We had now entered truly uncharted territory. By eliminating the most likely culprits, we'd cornered ourselves into confronting the unbelievable. All that remained on our list were two possibilities that twisted the very fabric of known physics: a classic unadorned black hole and the impossible gateway. From a distance, the two are almost perfect mimics. They both possess a gravitational pull so ferocious that nothing, not even light, can escape once it crosses the event horizon. They both bend space-time into a steep, inescapable well. How could we possibly tell them apart? The answer lay in a phenomenon that Einstein himself first predicted, a cosmic magic trick known as gravitational lensing. Any massive object, be it a star or a galaxy, warps the space around it, and this warped space acts like a lens, bending the path of light from more distant objects. By studying the precise way the light from a background star is distorted as it passes near our anomaly, we could map the exact shape of the gravitational field it was generating. A black hole, with its infinitely dense singularity, should produce a specific, well-understood pattern of lensing. But what about a wormhole? What would its signature look like? For years, nobody truly knew. A traversable wormhole is a creature of pure theory, requiring a substance known as exotic matter to prop its throat open matter with negative mass of gravitational repellent. The mathematics describing it were a thicket of impossibilities. But as our observational data was being gathered, a breakthrough was quietly occurring in a sterile supercomputing facility in Switzerland. A team of theoretical physicists led by Dr. Aris Thorne had finally cracked the code. They had built the first stable three-dimensional simulation of a traversable wormhole embedded in the chaotic environment of the galactic center. For the first time, we could see what a gateway stabilized by exotic matter would actually do to the universe around it. The simulation was a work of art, a ballet of equations rendered in light. It showed that the throat of the wormhole, the tunnel connecting two distant points in spacetime, would create a secondary lensing signature. It would produce a delicate shimmering halo of faint concentric rings of light, a gravitational echo, It was a pattern completely distinct from the single smeared arc of a black hole. Thorne's team had in essence drawn a perfect police sketch of their impossible suspect. Back at the Event Horizon Telescope headquarters, the observational team was stumped. Their new ultra-precise lensing data from the stars behind the anomaly showed a pattern that made no sense. It fit the profile of a black hole, yes, but there was something else. A faint residual distortion they couldn't account for. A ghost in the machine. It was noise they first assumed an instrumental artifact they would eventually filter out. They spent weeks trying to eliminate it, recalibrating, rerunning their models, but the phantom signal refused to vanish. It was real. Frustrated and at a dead end, they began searching for any new theoretical papers that might explain such a bizarre effect. And that is when they found Thorne's simulation. It was a moment that would be remembered in the annals of science, a convergence of pure theory and hard observation that happens perhaps once a century. They took their noisy, inexplicable lensing data and overlaid it with the predicted gravitational echo from Thorne's simulated wormhole. It was not a partial fit. It was not a close approximation. It was a perfect, breathtaking one-to-one match. The ghost in their data was the whisper of a distant star, its light having travelled for millennia, only to be bent into a series of spectral halos by the gaping maw of a tunnel through space-time itself. The implications were so immense, so staggering, that for a time no one in the room dared to speak. They had not merely failed to prove the anomaly was a black hole, they had discovered observational evidence that perfectly matched the signature of something far, far stranger. They had systematically ruled out every other possibility, and the one that remained was the one they had never truly believed was possible. But the universe, it seemed, had one final, even more profound revelation in store for us. Buried deep within the torrent of data from the James Webb Telescope, deeper even than the search for a thermal signature, was another signal, one so faint it was initially dismissed as pure statistical noise. A team dedicated to studying the very heart of the object, the point of infinite blackness, noticed a flicker. It was a subtle, rhythmic pulse in the extreme red end of the spectrum, an impossibly faint red-shifted signal that seemed to be emanating from the very centre of the event horizon. This, according to everything we understand about general relativity, is impossible. Nothing can escape from beyond an event horizon. No light, no information, no signal. It is the most absolute one-way border in all of creation. Unless, of course, it isn't a border. Unless it's a doorway. The signal was weak, pathetic. Even a mere handful of photons every few hours stretched and drained of their energy by an unimaginable journey. But it was there. And the only explanation that even began to make sense was that this light was not coming from the anomaly. It was coming through it. It was the light of a different patch of universe from the far side of the gateway, leaking through the throat and spilling out into our own cosmos. It was the ghostly echo of another place, another time. The red shift was immense, suggesting the light had travelled across a colossal, perhaps intergalactic distance. This wasn't just a gravitational signature anymore. This was a beacon. This was a message in a bottle tossed into the cosmic ocean from an unknown shore. We had set out to take a photograph of a monster to confirm the existence of a well-behaved black hole behaving strangely. We had followed a trail of breadcrumbs left by gravity and light, eliminating one suspect after another. And now, at the end of that path, we find ourselves staring at this. Evidence. Not proof, not yet. But evidence so powerful, so compelling, and so utterly alien that it forces us to reconsider the very nature of our reality. The question is no longer simply what this object is. We have stared into the abyss at the heart of our galaxy, and the abyss, it seems, has shown us a flicker of light from somewhere else. The question now is, where does it lead? And so, after a journey to the very edge of comprehension, we find ourselves here, standing before a locked door at the heart of the Milky Way, the key just beyond our reach. We have stared into the abyss surrounding Sagittarius A, into that maelstrom of warped light and shredded stars, and we have seen a ghost, a phantom in the data, a subtle anomaly in the endless dance of gravity and light that refuses to be dismissed. Is it truly a bridge to elsewhere, a shortcut across the cosmos carved by forces we are only beginning to name, Or is it merely a mirage, a trick of physics so extreme, so far beyond our terrestrial experience that it mimics the impossible? The truth is, we do not yet know. And for a species defined by its relentless need for answers, that uncertainty is both a profound frustration and a glorious gift. Because the search for this one object, this single candidate, for the most revolutionary discovery in human history, has already changed us in ways we're only starting to grasp. It has become a crucible for our science, a cosmic forge in which we have been forced to hammer our most trusted theories against the anvil of the unknown. Before this quest began, our understanding of the galactic centre, while impressive, was like a map drawn from a great distance. We knew the geography, the major landmarks, the titanic black hole holding court at the centre of it all. But the search for a wormhole's subtle signature demanded more. It demanded we become natives of that violent, luminous territory. It forced astrophysicists to move beyond elegant models and confront the messy, chaotic reality of a supermassive black hole's immediate environment. Every flicker of light, every slight polarization of a radio wave had to be interrogated with a new level of forensic intensity. We had to build simulations of such staggering complexity that they consumed the processing power of entire server farms for months, just to render a few seconds of virtual time in that abyss. These weren't just prettier pictures, they were new realities' digital testbeds where we could finally distinguish the plausible from the fantastical. We learned to map the magnetic field lines near the event horizon with a precision that would have been unthinkable a decade ago, not as a mere academic exercise, but because a wormhole's throat might twist those fields in a unique and telltale way. We charted the swirling currents of superheated plasma in the accretion disk, tracking individual hotspots as they orbited at nearly the speed of light. We did this because their orbits, their very existence, could betray the presence of a gravitational field subtly different from that of a standard solid black hole. This relentless pursuit of an anomaly has in a beautiful paradox given us the most complete and robust picture of what a normal supermassive black hole environment looks like. We have refined our understanding of accretion physics, of how black holes feed, and how they launch their colossal jets of energy across thousands of light years. The search for a gateway to another universe has in the end given us a far deeper, more intimate understanding of our own. It has been a lesson in cosmic humility, reminding us that even the most familiar objects in our celestial bestiary hold secrets that can only be unlocked when we dare to ask the most audacious questions. But the impact resonates far deeper than just observational astronomy. This journey has taken us to the bedrock of reality itself, to the foundational principles laid down by Albert Einstein a century ago, General Relativity. His masterwork has been our unerring guide through the cosmos, predicting everything from the orbit of Mercury to the existence of gravitational waves. It has passed every test we have ever thrown at it, until perhaps now. The region around Sagittarius A is not just another testing ground. It is the ultimate arena, the final trial by fire for Einstein's laws. Here gravity is not a gentle slope, but a sheer cliff, a place where space-time is stretched and twisted to its breaking point. A standard black hole, a so-called Kerr black hole, is a creature born entirely from the mathematics of general relativity. It is in a sense the theory's most extreme and perfect child. A wormhole, on the other hand, is something else. It is a rebel, a solution that the equations allow, but that seems to require a tryst with some other stranger physics to exist. Looking for a wormhole, therefore, is not just about finding a new object. It is about looking for the subtle cracks in Einstein's magnificent edifice. Every photon we captured with the Event Horizon telescope, every wobble in the orbit of the star S2 we tracked for decades, every pulse of energy from that enigmatic core was scrutinized not just for what it was, but for what it wasn't. Was the shadow of the event horizon perfectly circular as a spinning black hole demands, or was it infinitesimally distorted? Was the light bent in precisely the way the equations predicted, or was there an extra tremor, an unexpected shimmer that hinted at a topology more complex than a simple puncture in space-time? This intense pressure has forced theorists to push general relativity into unexplored territory, to calculate the precise observable signatures that would prove Einstein's theory incomplete. They have had to game out the catastrophic consequences of a star falling not into a black hole but through a wormhole. What would its death cries sound like in the language of gravitational waves? They have had to model the bizarre echoes in space-time that might reverberate from a traversable tunnel, a distinct signal that would be an unambiguous smoking gun. In searching for a deviation from the theory, we have come to appreciate its power and resilience more than ever before. We have put Einstein on trial in the highest court of the universe, and while the jury is still out, the proceedings themselves have revealed the breathtaking scope and subtlety of his vision. The candidate near Sagittarius A remains the single most profound and tantalizing piece of evidence that suggests there might be a page missing from his cosmic rulebook, and that missing page may well be the introduction to an entirely new story, the story of quantum gravity. For decades, the two great pillars of modern physics have stood in defiant isolation: General Relativity, the sweeping epic of the very large of stars, galaxies, and the expanding universe, and quantum mechanics, the strange paradoxical tale of the very small of atoms, electrons, and the probabilistic fuzziness of reality. Both theories work perfectly in their own domains, but where they meet in the heart of a black hole or the first instant of the Big Bang, the mathematics breaks down into nonsense. The universe we know is not two separate stories. There must be a single unified theory, a theory of everything that can write the laws of the cosmos in one elegant equation. A wormhole, should it exist, is not just a tunnel through space, but a physical bridge between these two irreconcilable worlds. The very concept of a stable traversable wormhole hinges on the existence of so-called exotic matter, a substance with negative energy density that would prop the tunnel open, preventing it from collapsing into a singularity. Such matter is forbidden by classical physics, a nonsensical idea. But in the bizarre world of quantum mechanics, under very specific conditions, fleeting pockets of negative energy are not only possible, they are an observed reality in the laboratory. The candidate near our galactic core therefore has served as a cosmic beacon for theorists working on the grand unification. It has taken their abstract ideas from the vibrating filaments of string theory to the granular space-time of loop quantum gravity and dragged them out of the realm of pure mathematics and into the world of testable predictions. Suddenly, their esoteric equations were being asked a very concrete question. If your theory is correct, what should we see when we look at the centre of the Milky Way? Could the extra dimensions predicted by string theory manifest as specific gravitational lensing effects? Could the quantum foam at the heart of the wormhole's throat leak a unique form of radiation, a whisper of the underlying quantum reality of space-time itself? This object of interest has become a focal point, a Rosetta Stone that might allow us to translate the language of quantum mechanics into the language of cosmology. It has motivated a new generation of physicists to think not just about what a wormhole is, but what it's made of. At the most fundamental level, the hunt has transformed the search for quantum gravity from a philosophical pursuit into an observational science. We are no longer just thinking about the nature of reality. For the first time, we are looking for it there in the heart of our own galaxy. So where do we go from here? How do we turn this tantalizing possibility into a definitive answer? The path forward is as ambitious as the question itself. It requires a new generation of eyes on the universe instruments with the power to see not just more, but differently. The Event Horizon Telescope must grow, expanding its network of dishes across the globe and even perhaps into space itself. An orbiting radio telescope synchronized with its terrestrial counterparts would create a baseline as wide as the Earth, sharpening our vision to a degree where we could resolve not just the shadow of the event horizon, but the intricate swirling structures of light at its very edge. We need to see the movie, not just the snapshot, to track changes in that infernal region in real time, looking for the telltale flicker of an object passing into, or perhaps even out of the mysterious maw. But light alone will never be enough. To truly map the gravitational landscape of the galactic core, we must listen to the symphony of space-time itself. We need gravitational wave observatories with a sensitivity that dwarfs our current capabilities. Projects like the Laser Interferometer Space Antenna, or LISA, will place detectors millions of miles apart in space, creating a celestial observatory capable of hearing the low-frequency rumble of supermassive objects. It would be able to detect the subtle gravitational quivers from a star being spaghettified by a black hole, or the unique echoing chirp that theorists predict would emanate from a perturbed wormhole. We must open new windows looking for neutrinos, cosmic rays, or even particles completely unknown to science that might be the exhaust fumes of a passage through space-time. It will demand a coordinated multi-messenger assault where we point all our instruments, all our senses at that one spot in the sky and watch and listen and wait for the universe to betray its deepest secret. And as our technology evolves, so too must our ideas. The data that will pour in from these future observatories will be so vast, so complex that human minds alone may not be able to decipher it. We will need sophisticated artificial intelligence algorithms trained to find the patterns we are not clever enough to anticipate, to see the signature of new physics hidden within the cosmic noise. And perhaps above all, we need a new theoretical framework, a conceptual breakthrough as profound as relativity itself. It may be that we are looking at the data with the wrong vocabulary, trying to read a new language with an old alphabet. The final confirmation may not come from a telescope, but from the mind of a theorist who provides us with a new way to see a new context in which all these strange disparate clues suddenly and beautifully snap into place. In the end, this quest, this long journey we have taken together to the brink of the impossible transcends the search for a single object. It is a story about the fundamental nature of exploration itself. Whether that anomaly at the heart of our galaxy is a true gateway or a magnificent cosmic illusion almost ceases to be the point. The true discovery is what the pursuit has awakened in us. It has forced us to the very limits of our technology and our intellect, and in doing so has shown us how much further we have to go. It has united scientists across disciplines and borders, focusing the power of our collective curiosity onto a single, unimaginably distant point of light. It has reminded us that the universe is not only stranger than we imagine, but stranger than we can imagine. The greatest discoveries are rarely the final answer to an old question. They are the ones that reveal a whole new landscape of questions we never even knew how to ask. This is the legacy of our search. It is a testament to the indomitable, unquenchable human spirit, the part of us that is never satisfied with the world as it is, but must always ask what lies beyond. That impulse is our species' greatest gift. It is what brought us out of the caves and onto the plains. It is what led us to cross the oceans and touch the moon. And it is what now drives us to peer into the heart of a black hole, searching for a passage to the stars. The final answer from Sagittarius A may not come in our lifetimes, but the journey has already reshaped our map of reality. It has left us with a profound and stirring truth that the act of reaching for the unknown is what truly defines us, and that even in the face of cosmic uncertainty, the quest itself is the most magnificent discovery of all. It inspires us, it challenges us, and it assures us that for a species like ours, the age of wonder is never ever over.